Good morning, Doctor. I'm Antonio Frank. I'm going to present a paper on non-orthogonal optical multiplexing powered by deep learning. This paper which I'm going to present is written by the following: Wang Pan, Jian Wei Yi, Fan Zhang, Pengabi Zhu, Ok Zhu, Yi Zhu, and Yun Quinn. These are the authors of this paper, which I'm going to present, and I'm going to present how non-orthogonal optical multiplexing is powered by deep learning. So non-orthogonal multiplexing is a technique in telecommunications that is used to combine non-orthogonal signals or streams or light fields from different sources and being propagated onto a single transmission medium. And the transmission medium which we shall be using, it is called an MMF transmission medium. It's a type of optical fiber cable that is used to propagate the non-orthogonal signals or light fields. Now, the primary goal of multiplexing is to utilize the available bandwidth, thereby maximizing the channel capacity so that there is a high efficiency or high degree of throughput that is required by that transmission medium or an MMF. Now, as you see from this diagram here above here, we see the characteristics of non-orthogonal signals. As you can see, they have the same amplitude, they have the same wavelength, they have the same frequency, they have the same phase, and they have the same polarization or orientations. And we shall see that this play a role in the imposing or in the incorporation or in the how does the information is retrieved from these characteristics, as we shall see later. Non-orthogonal multiplexing over an MMF refers to the use of non-orthogonal techniques for transmitting optical signals over an MMF. MMF is multi fiber. It's a type of an optical fiber cable that is used to propagate and transfer. Is to propagate and transfer the optical signals. Or in this here, we shall be using the non-orthogonal light fields, thereby allowing them to pass through this cable. Orthogonality comes at actually the opposite of orthogonal. Non-orthogonal is orthogonality. Orthogonal, it is the normal signal multiplexing. There's normal signal multiplexing, but here we are now using the non-orthogonal component, non-orthogonal type of multiplexing. So orthogonality, it brings about, it has the advantage that it has a disadvantage in that there is reduced complexity of signal post-processing at the demultiplexing spot. So this is the orthogonality of the signals could be good, but it has that disadvantage of demultiplexing at the rear end of the MMF. So another limitation of orthogonal multiplexing is that it uses techniques of frequency division multiplexing, partial division multiplexing, polarization division multiplexing, and model division multiplexing. The division nature of the orthogonal techniques pose a great challenge and impose a limit in multiplexing the channel. So this breaking nature was a step for the realization of non-orthogonal optical multiplexing over an MMF. So it becomes a challenge to decode information from non-orthogonal optical signals with the same wavelength, polarization, amplitude, and phase. This is because of the inverse transmission matrix that fails to do the task as seen in the diagram. Now, when it comes to demultiplexing or propagating these signals from the rear end of the MMF, there is a problem of demultiplexing because of the inverse. If at all we are supposed to use, because the inverse transmission matrix is used in the orthogonal multiplexing. But if we are to use the inverse matrix for non-orthogonal multiplexing, optical multiplexing, it will be a challenge. It will fail, as we see from this diagram. Now you see from diagram A, we see the input signals or the input light fields being multiplexed, and then the multiplexed signal or the multiplexed light field is being propagated onto this multimode fiber. And then at the spot of the single shot intensity detection, the single intensity detection, it is a spot where this signal here, or the light intensity, is picked up and then propagated to its destination. But before it reaches, or before it is being demultiplexed, or the proceeding processes, there is incorporation of a transmission matrix. The transmission matrix here fails the propagation of this signal to its destination. So, but the incorporation of a neural network after this spot here, we see that the signal is pushed to the destination. So you see how neural network is being incorporated in the effective multiplexing of the non-orthogonal signal. So we shall see how this neural network here in the next slide, how this neural network here being used to propagate this signal, and then all the light field with different information and different dimensions of phase and phase polarization and the amplitude. So this has been the explanation of the previous slides, how the inverse matrix fails when you apply non-orthogonal optical signals or non-orthogonal optical light fields, how that transmission matrix fails to pick up or to decode the information brought by that single signal from the MMFP cable. So then figure B shows how a neural network is being able to retrieve the information from the non-orthogonal signal. Therefore, deep learning neural network mechanism developed to decode information in the encoded orthogonal, because that information, when it is moving after the multiplexing, the light fields of the non-orthogonal characteristic comes with the encoded information. That encoded information has to be decoded by the neural network. And that neural network called the SLNet. SLNet is a speckle light and field retrieval network. It is used to retrieve information from that multiplexed signal or the multiplexed light field, and then it encodes that information, and then it propagates it to the output. So multiplexing of non-orthogonal optical signals or optical light fields involve the incorporation of scene images, as we shall see how images are being part of the information that is propagated onto the medium. And then that information, it is fed into the neural network or the deep learning neural network. And then that information is convolved, and then other classification algorithms are applied on that. So a well-trained neural network can retrieve encoded information from non-orthogonal channels by merely using short output information that can be decoded as well. So we have this function here. The function this function R theta is a function that really helps in the matching. It is a function that is used in the neural network. This function here, it helps to map the very many input non-orthogonal light fields and propagate and maps it to one orthogonal light field output. So this function here, R theta equals to arg mean the magnitude of R theta ik. Ik here, it is the output signal, the output light field. And then CNK, those are the pool of non-orthogonal light fields that are being subjected to a multiplexer. So R theta, it is a mapping function determined by the weight of the deep learning network. So CNK and IK, it is a data set. It is a data set Q. So these elements here belong to this data set Q. Are members, this symbol means are members of Q. So I've talked about the weights on the network. So theta, it is a member of the sigma, and sigma means all the weights or parameters, all the weight parameters on the network. So I will train RQ, R theta. We have said R theta, it is a function that maps the input light fields to the many-to-one relationship, and it is used to retrieve information encoded on the input non-orthogonal light fields within the amplitude and phase dimensions. So SNK, this means the many light fields. Then IK means a single speckle output or a single output light field that has been multiplexed. So this neural network builds an approximate relation that maps the speckle density at the distal end of MMP to the distributions of amplitude and phase of several input light fields. That's what I'm from explaining the mapping. So this statement shows the mapping. The training of the deep learning neural network relies on the data set using pairs of output speckles with their corresponding input wavefronts. Now, this function here, or this expression here, it is the demultiplexing expression. The demultiplexing expression. So, h raised to power -1 into I is the same as, this is the relationship that maps plus times I is the single speckle output or the multiplexed channel, the multiplexed light field. Structure of the deep learning neural network for non-orthogonal optical multiplexing. So the neural network is capable of retrieving information from non-orthogonal optical multiplexing from a single output at the distal end of the MMF. So the neural network will retrieve the encoded information, and then it will decode that information that has been propagated or superimposed onto it, and then it will invoke a number of functions, activation functions, the convolving, and then an output will be generated. So multiple phase and multiple amplitude and phase encoded information mediated by arbitrary combination of polarization can effectively be retrieved by EtherNet after propagating the MMF. So as I said, as the light fields are being superimposed onto the speckle output, or that single channel or single light field that is being propagated onto the MMF, but at the end of an MMF, there is what we call a single speckle output. Now, a single speckle output, it is a spot where this single light field is being received. Now, once it is being received, it will be demultiplexed. But once it is being demultiplexed, the neural network receives that information that has been encoded on those multiplexed light fields, and and the encoded information. Remember, we are talking about non-orthogonal optical signals. Non-orthogonal optical signals have characteristics. So these signals, they undergo, or they have characteristics of polarization. Polarization, those are different orientations. Remember, the signals are many, or light fields are many. So they have that characteristic of polarization. Polarization to different orientations. So the combination of different polarizations can be part of the input to be fed into the what? Into the neural network. So the neural network consists of a fully connected FC layer and a res unit, a combination of residual neural network and convolution network. The FC layer of this neural network, or SLNet, is used to enhance the fitting and generalization habit of the neural network. So the neural network has a number of blocks. We have the residual block, the residual convolutional block, the residual transposed convolutional block, and then the convolution layer. It helps in channel compressing. How the orthogonal optical multiplexing neural network works. It receives light field channels that have an arbitrary combination of polarization values. So they are multiplexed. Then each light field consists of the encoded information in both amplitude and phase dimensions. This results into multiplexing 4 channels transmitting different information. Then the neural network relies on supervised learning algorithm during that process of training. The network outputs predicted for matrices containing both the encoded amplitude and phase information from the original two original light field channels. This means that the encoded information in the orthogonal multiplexing is orthogonal labeled. So once there is a successful once there is a successful generation of the image, or successful classification, or successful invoking of various operations on these light channels on this deep learning neural network, then we shall say that the multiplexing is orthogonally labeled when the network is trained. From the diagram below, we shall see the perception of the network feed-forward architecture, where the information flows from a fully connected layer to the inner layers and then down to the output convolution layers. As you see from the first diagram here, this first diagram shows how different light fields with different information encoded on how it is being propagated how it is going to be multiplexed, having different characteristics of polarization. These arrows mean polarization, the different orientations of these light fields. As you see, some are circular, some are horizontal, some are diagonal. So as they are being multiplexed, remember they have information within them. Now this information is being multiplexed and then propagated onto this MF channel. And then the MF channel at its end, the rear end, has what we call the speckle output. Now this speckle output is the one that really does the demultiplexing. The demultiplexing, the signals that are being demultiplexed are being superimposed onto this SLNet. SLNet is the deep learning neural network that helps to perform operations of the demultiplexed light fields. So this spot here, this is the diagram here that shows the step here. So the signal up from the speckle output is being superimposed onto this neural network, this SLNet, and then various operations are worked upon onto this neural network. As you see, convolutions happen here. The other function, which I'll show you the other function with the weight, it also happens at this stage. The mapping function, the RQ, happens at this spot here. So the convolution, that's why you see cells here are being convolved using these various blocks of the convolution. This is the residual convolution block. This is the residual transpose convolutional block, and this is the convolution layer. So convolution layer will itself internal compressing. So after our light fields are being operated upon this SLNet, now we shall get the output here. So you see that there is some good kind of classification that has happened here. So these are the images that belong to amplitude, to that signal with the first amplitude, the light field with the second amplitude, like that. Now performance of the SLNet, as we have said, two multiplex light field channels. These are non-orthogonal channels with habitual combination polarization states are used during the training. Then 4 channels are encoded. Then the relative fidelity, it is a value that is used to measure the accuracy and the performance of this SLNet, or the deep learning neural network, and it's provided by Bayesian correlation coefficient. Now, a lot of different polarizations are considered, including linear, circular, and elliptical polarizations. Now, these are different polarizations of the light fields, that are being superimposed onto the SLNet, or the deep learning neural network. The results show that the relative fidelity for all the input measured by PCC after training process is seen to be larger than 0.97 after 100 epochs. 100 epochs, those are different iterations of the SLNet. You get the output. If the output is not sufficient enough, is not generating correct results, again, you feed it back into the what? Into the neural network. Like that, 100 times, until you get an accuracy or a higher value. So the average fidelity after performing a number of iterations across a number of various polarization values or arbitrary polarization values, we shall see that the performance of that and it's of our Ethernet will reach up to 0.98. Now, this shows an excellent robustness of the orthogonal optical multiplex with respect to arbitrary polarization values. So this figure here, or this diagram here, shows how our SL or deep learning neural network has been working, how it has been, the performance of the neural network across light fields of all these different orientations. That's why you see now, as you can see now here, the orientation of the light signal or the light field of 10 degrees. This is somehow red, some kind of purple, as you can see from this. It goes this the first curve here that is purple. You'll see that it is around 97 something. So you see, across all these various orientations, they all merge almost at the same value. Almost at the same value. This is a 3D or XYZ, Z coordinate system that emulates this curve here. This ROC receiver operating curve. So as you can see here from the x-axis here, the x-axis we see the characteristics of all the dimensions of amplitude and phase. Amplitude and phase with a different what? With a different polarization. You see that the value here of these signals here, or the light fields here, almost around 0.9 something, 0.978 like that. It almost emulates the result of this ROC curve here, ROC curve. So we are going to see the performance of CellNet with respect to the labeled data. So first, 4 scale images are multiplexed in the amplitude and phase dimension using the same polarization, and we shall see that almost similar outputs will be generated. And we shall see another parameter that is used to output the value, the performance value of our SLNet, and that parameter is called the SIM, Structure Similarity Index measure. Previously, we've been seeing Bayesian collision coefficient that is used to give us a value that is used to determine the performance of the SLNet. This time, we shall also be seeing how the model is performing with respect to structure similarity index measure. So you see now here, now this is the ground truth, how the images appear as per in our normal environment. Now, after superimposing the images onto the SLNet or the deep learning neural network, we shall see that the performance, as you see, the performance is quite better. Now, previously here, we've not been superimposing our neural network any kind of labeled data. We've been using just parameters of amplitude, phase, and polarization. But here we are now using the real images, how our neural network is going to be performing when we are feeding it with images, or how it performs, how it is performing after decoding the information encoded under non-orthogonal light fields, and the information are the images we are talking about. So we shall see that now SSM stroke PCC, like now from this first image here, the value of SS of IM is 0.973 stroke 0.996. So our neural network, deep learning neural network, it is performing with the rest, its performance, it is correlating. Its performance, when we are feeding it with images, it is correlating with the performance without images, or when the non-orthogonal signals are being fed into the machine with various parameters of amplitude, phase, and polarization. So previously we will not be feeding it with images. Now we are feeding it with images, and the performance is correlating. So here the polarization is 0. Here the polarization is 90. And here the polarization is 10. And here it is ellipse. Ellipse. And you see how this one shows. By the way, here we are using the non-orthogonal multiplexing over 1 millimeter MMF cable, optical fiber cable. Now here we see the performance of our neural network. We respect the training data, but now we have increased the length of the cable. Now the cable here is using 50 meters. Now here you see that the performance somehow is deteriorating. Previously we've been seeing here is for the first polarization, or the first image here is 0.973. Now for the second, when you have increased the length of the cable, we shall see now here the performance is now somehow goes down. It goes down a minimum, let's say a negligible, but still it shows that there is a depreciation of the performance of the neural network. Now this is the performance of the neural network, or the SLNet on the unseen data, or the I can call it the evaluation data, or the training, not the training, the test data set. So still, so previously we've been feeding here, as you see from the training data, now here we are feeding different data, different information, or our neural network is encoding or decoding different information from the what? From the non-orthogonal signals. And you see that the performance here is still becoming, is still somehow better. Still actually better, because 0.88 against 0.93. This shows that the performance of the non-orthogonal multiplexing over an MMP optical fiber cable with respect to the neural network is performing to the best. So you see here, phase here we are in dimensions of phase only, or dimensions of amplitude and phase, amplitude and phase. And you see that it is trying to really generate the necessary output that really matches with the input. It is really performing there, generating the output to the best. So the results above show successful non-orthogonal optical multiplexing over an MFP multi-fiber cable powered by deep learning, utilizing the SLNet up to 5 optical degrees of freedom These are simple characteristics of the non-orthogonal optical light fields. And you will see from the experiments we can conclude that SLNet achieved a high fidelity of 98% as far as information retrieval and processing, or invoking different functions and methods, convolutions, giving it various activation functions. We see that it really performs to the best here. Challenges of this SLNet: the performance depreciates as the length of the cable increases, as we have seen. As the cable increases in length, the performance depreciates or goes down. The MMF is affected by environmental conditions that brings about to scattering properties. Applications: non-orthogonal optical multiplexing. It is applied in enhancing the high throughput of MMFs for communication and information processing, and therefore improving the capacity of optical systems. So we have seen the performance of non-orthogonal multiplexing as far as its performance is concerned in connection with the neural network, and we have seen that it's performing to the best. So we see that if once that the operation is performed, then it can be incorporated in enabling a high throughput of these optical fiber cables. Now this super resolution, so it is applied whereby is applied to generate high resolution images from low resolution images or inputs. Anomaly detection, feature extraction and classification. As we have seen, there is classification that happened during I showed you in my presentation. So classification is performed with respect to the input data, and then various machine learning algorithms can be applied, and then classification happens. So if we have performed a linear regression prediction, then this algorithm can perform classifications of the input data set reversed into different categories. Okay, doctor, that has been my presentation. It has been long, but that's what I've been managed to present to you, doctor. Thank you so much.